Good morning, everybody. I'm sad. The last lecture, right? I mean, next time I see you, I'm going to be torturing you with an exam. Sad also, but not for me. But yeah, that's big. Let's see here. Quiz sheets, right? Want to get those in as soon as you can. We will next meet on Thursday for the exam, normal time and, exam, all that kind of stuff. And then after that, it's next Thursday. I keep trying to tell you this, and I hope it sinks in, right? Next Thursday at 9 o'clock, not 9:30, right? 9 o'clock. Very, very important. Okay, so got all that out of the way. Got quiz sheets, all that kind of stuff. Did I do this last time where I broke it up by chapter? Yeah, I did, when I did the announcement.
I think you told us. You did it in class.
Did it in class, so I managed to actually do it ahead of time this time. It's kind of a miracle. But I did break it up by chapter where I put like 29, I put the modern physics stuff kind of together rather than breaking it all up. So on the last exam, did I write down after the question the topic, or at least the chapter title that it came from? Did I? Did I put it on the board?
Yeah.
I put it on board. Did that help?
Yes.
Because I didn't get any feedback from anybody. And I was kind of waiting for somebody to tell me that it was the best thing that ever happened to them in their lives, or it just didn't matter or whatever, but I didn't hear anything. I'm trying to remember. I think maybe I put the topic actually on the exam this time. Like question and then just like, and not these exact topics, but just like relativity, quantum mechanics, or nuclear physics, right? Just to give you some, or I hope I did that. If not, I guess I'll be writing it on the board again. But I mean, it helped those that it helped, and the rest of you didn't care. It didn't have a negative effect on you. Okay. Right? You didn't assume like I didn't write down the wrong topic. Okay, all right, good. All right. So before we get into like questions from homework or something like that, because I have a feeling I've had people emailing me saying, Mr. Vail, cover this one, cover this one, cover it. So I'm going to start actually. But before we get into specific questions, you have 2 questions on relativity, right? One each on time dilation and length contraction. So make sure you remember your definitions for proper length, proper time, okay? The questions I'm hoping are clear and straightforward for you. I guess we're going to find out, right? Electron configuration. By that I mean I'm going to ask you about an element, and I'm going to want you to write out its electron configuration. Or tell me how many electrons are in p orbitals or something like that, right? I did not attach a periodic table of the elements to the exam, okay? We've got the one up here. If this is difficult for you to see, let me know during the exam, and I'll just go run and grab a periodic table for you from chemistry or something like that, right? So you can have it right with you, but the problem isn't designed to be that taxing. And then the rest of this stuff we'll probably cover. Photoelectric effects, photons, work energies, or work function, be able to convert electron volts into joules, that kind of stuff. All right, so like I said, by request, I'm going to start, and this problem, I totally forgot what number it was. See if I can find it. I wrote everything down except the problem number. I think it was this chapter. Yep. This is the one that came in by request. Okay. And so let's see if we can't dive in and figure out what's going on here. Okay. Start with the end in mind. What are we being asked to find? What is the biologically equivalent dose? All right. So now I have to review some stuff. There's activity. There's what I like to think of dose. It's absorbed dose. And then there is dose equivalent. All right. So what units is activity usually given in? What does activity measure? Activity? It's decays per time, isn't it? And in becquerels or curies, absorbed dose. That was a joule per kilo, it was like energy per mass, wasn't it? And that was in grays, or you could do it in rads. And then the dose equivalent is in sieverts, I remember that, or rems. But this one was funny, and I always get this kind of like, I don't know, wrong, right? The dose equivalent, is that equal to the absorbed dose divided by the factor, or is it multiplied by the factor? Let's see, for alpha particles, it's 20 divided by 20. Yes, I think I got that right. Okay, I would have to look on my cheat sheet to be sure. Is it multiply? See, these are things that I never do. Where is my cheat sheet for this? Right here. Oop. Right here. Absorb dose. It's the other way around. Darn it. When I was so sure. So RBE or Q factor. Either way. There we go. Okay, so now that I'm oriented properly, what the heck have I got here? I've got, what's the millicuries? What's that a measure of? There's my activity, right? And they want me to get to this thing down here, the biologically equivalent dose. Sure, that's another way to say it. Why not just say dose equivalent? How are we going to get there? Like, what are the stepping stones from an activity to a dose equivalent? Let's see, we got to go through absorbed dose, don't we? Like, we kind of just have to step our way down this ladder. And that's good because I've been given an energy, the 2.5 mega electron volts, and I know the mass of my sample, right? So I'm feeling like a direction I need to strike out towards is figuring out what my absorbed dose is so that I can then find my dose equivalent in sieverts. Did they tell me what kind of, what the radiation was? Gamma rays, yeah, we're good. Okay, so with all of that in mind, right, I'm going to start with my activity. It was 5 millicuries. What does milli mean? 10 to the minus 3, right? So this is 5 times 10 to the minus 3 curies. And I need to get into becquerels, need to get into number of events per time. And I went and looked up the conversion factor. In 1 curie, there are 3.7 times 10 to the 10 becquerels. So I went and calculated that. I did my work ahead of time. 1.85 times 10 to the 8 becquerels. So that's the number of events that I have, and I know that a becquerel is a decay per second, right? They, in the problem, stated that we want the dose equivalent over 1 hour. So that's how many gamma rays I'm getting per second. And then I want to know the total number of gamma rays in an hour. Multiply. There's 3,600 seconds in 1 hour, right? And so I got my total number, total events. It's supposed to be an E, that didn't work out right. Events and this scared me, 6.66 times 10 to the 11 decays, or events, right? That's an ominous number in our culture. Okay, so now that I know how many gamma rays happen in an hour, I can find out what the total energy is. Because they told me that it's 5 mega electron volts per decay. They messed me up the first time I tried this because they gave me some information I didn't need to know, right? Cobalt-60 emit 2 gamma rays. So I thought, oh, well then I have to double the number of events, right? Like every time, but that's not what they did in their solution. I actually had to go look at the solution to see if it was a factor of 2 off. So I think they made a mistake, but we'll go with it. 2.5 total mega electron volts for both of those gamma rays coming out per event. All right, so how do I find the total energy? I can multiply, right? Again, I feel like this problem is a bunch of chapter 1 conversion factors strung together, right? Because I'm basically just kind of converting from units to units as I go. For every 1 decay, right? No, there was more than 1. 6.66 times 10 to the 11 decays, right, is going to get me my answer is going to get me my total energy in mega electron volts, isn't it? But a gray, just looking ahead, a gray is not mega electron volts, it's joules. So now I've got to convert that, right? So, for every 1 mega electron volt, I went and looked up the conversion factor, it's 1.602 times 10 to the minus 13 joules. There's several ways you can go about doing that, but I just asked Google what a mega electron volt is. And when I finally did all of that, I got 0.267 joules worth of energy. Okay, so now I know my total energy that the cobalt-60 source delivered, and I know the total energy, or I know the mass of my sample. What was it? 0.15 kilograms? So my grays are going to be equal to 0.0267 joules divided by I already forgot the number, 150 kilograms to get me 1.78 grays. And that is my absorbed dose. It's not what they want. They want the dose equivalent, so I've got to take into account the fact that these are gamma rays, right? And so, going back, right, I know that the RBE or Q factor for gamma rays is 1, which means that my dose equivalent is going to be 1.78 sieverts. Gamma rays is kind of nice. It's whatever your grays are, that's your sieverts. You don't have to worry about it. I believe this problem is annoying. Yeah, they want us to answer in rems, right? But it's a factor of 100 different between the two. And so in 1 sievert, there are 100 rem. So this answer turns out to be 170. So again, I'm not sure that the physics of this problem was that much. It was the confusion that surrounds converting between different kinds of radiation units. And I don't think it's that the units themselves are confusing, it's just it's a lot of new terminology and a lot of new ideas, right? And not being familiar with a gray or a sievert or anything. Very different from, like, I know you in 2A you weren't familiar with meters per second either, but at least meters and seconds, you've heard of those things before. You associate them with distances and times. It's hard to make an association for something that you've never ever heard of before. So, practice a little bit, make sure that you've got that little chart that I had in class, right, about which one's an absorbed dose and the fact that a gray is a joule per kilogram. You don't need to know the conversions between becquerels and curies, because if you need to know that on the exam, they've either given it to you or you can ask me for it on the student conversion factors, right? All right. Other questions, comments, and concerns? Yeah.
What is like the
For gamma rays? Why is it?
Yeah.
I have no idea. Gamma is the most biologically intensive of the radiation types, and so it means that it's better at delivering its energy to tissue. So I think the one came out of gamma's the worst. It's a 1-for-1 energy transfer back and forth, whereas beta and alpha were much worse at delivering their energy. They have a certain amount of energy, but that energy doesn't necessarily get delivered to tissue as effectively. And by making those numbers bigger, it lowers the amount of energy that's actually delivered. I kind of showed that in class a little bit, how when we calculated the dose equivalent in gamma rays versus alpha particles for the same energy, it turned out to be 20 times less energy was deposited in the tissue. So it's always felt a little bit backwards in my mind. Like gamma's the most biologically effective, it's best at delivering its energy, so it should have the highest number. But that's, for whatever reason, that's not how they defined it. And I'm pretty sure they standardized on gamma being 1. Because I've never... Yeah, I am pretty sure I've never seen an RBE factor for gamma that isn't 1. Alpha and beta I've seen different numbers for. But gamma I don't think I've ever seen anything different than 1. But this isn't my day job either, so a nuclear physicist can correct me. Are there any nuclear physicists in the room? No? Okay, gamma's 1. Yeah.
Could you go over
Nuclear power. The conceptual question is on nuclear power, isn't it? Okay. What's the difference between a nuclear power plant and a coffee maker? Nothing. They both, make steam. They boil hot water, right? It's just the coffee maker uses electric coil and the nuclear power plant uses the reactor. So really, everything comes down to the reactor side, the thing that's making the heat. And in the case of a nuclear power plant, where are we getting the heat from? Like specifically? The fission reaction, right? The fission decay of usually uranium. I say usually. There are no power plants really, I was going to say across the world, there might be a couple. Most power plants run off of uranium-235. Plutonium needs to be made, bred in a breeder reactor, and then it's a little bit more problematic to deal with on an engineering side than the uranium is. So most are uranium-235. So we've got these fission, we've got the decay of naturally unstable uranium-235 that is generating radioactive waste and energy, thermal energy that comes out of those reactions. We're trading the mass that's tied up in the binding energy for energy E equals mc squared. So that heat is then captured somehow, some way by the reactor. And what is the part of the reactor that is dedicated to capturing that energy so it can be moved on to the rest of the process? Remember what it's called? Starts with an M, ends with er. Moderator. So you know these parts, right? So we have the fuel, right? The thing that's giving off the heat, okay? We have the moderator, which is the thing that is transferring that thermal energy away from the reactor, away from the fuel, to the other parts of the system. The condenser, you don't really need to worry about any of that, right? Okay? So we have fuel rods, we have the moderator, and what's the other thing that we have in a reactor? Very important. The control rods, right? And based on the name, what do the control rods do? They control the reaction. So how do they do that? What is a feature of control rods that's very, very important? They absorb neutrons, right? It acts like a neutron sponge, okay? By capturing neutrons, and if the control rod has taken a neutron that's coming out of a fission event, that neutron isn't available anymore to do anything, right? It's been caught, okay? So the control rods capture those neutrons and prevent them from doing any more fission events, right? And sort of how far you put the control rods in and out of the reactor determines how many of those excess neutrons are caught and determines the energy that's coming off of the reactor. Very important in reactor design is to maintain your moderator, right? You need this moderator to continuously be capturing this energy. And there's an Achilles heel that exists in more or less all designs that haven't been built in the last 20 years, okay? What's the Achilles heel of a nuclear plant? The thing you don't ever want to have stop. The cooling pumps, right? Those pumps that are responsible for moving the moderator around, okay? Moderator in almost all plants is water. It's just too good at soaking up energy. After that, the moderator goes to a heat exchanger, boils water, makes steam, turn turbine, get social media, whatever, video, whatever the downstream product happens. Did I answer your question sufficiently? Can reactors go boom? Yes and no. They can go boom, but is it a nuclear boom? No. It's always a conventional boom. Other questions? everybody ask at once. Yeah.
Could you come up with the last problem in chapter 31?
31 last problem. Phosphates. Isotope is often used to pinpoint location of tumors. Half-life of phosphate 32 is that many days. Wow. After a small amount is ingested, how long will it take for almost all of it to go away? So key thing that's sort of tipping me off that this is a half-life problem is they're asking about time in the context of they use the word half-life in the problem, right? Okay, but they're asking for how long. They're asking for a time. Okay? And we had a way of determining what that time was. We knew that the rate or number remaining equation looked like that, and then when we solved that, oh boy, from memory, this ends up being negative the natural log of r over r naught divided by the decay constant. Did I get that right? Wow. Okay. So I gotta get some of these pieces together. Let's do decay constant first because it seems easier. Because they gave me the half-life, that was equal to the natural log of 2 all over the decay constant, wasn't it? So my decay constant is going to be natural log of 2 divided by the half-life. Is natural log of 2 like, is it 0.693? I use that so much in my physics career that it kind of stuck. Half-life's not the only place where the natural log of 2 crops up. Any exponential gain or decay, it's always looking somewhere. And then if I put in 14.3 days, that means that my final answer, the unit for time, will be days, right? Whatever unit I have on my half-life or decay constant is the one that eventually flips up and gets in the right direction. So I don't have to convert to seconds or years or any of that kind of stuff. So I get a number. That's my number. All right, so I've got that number. It's going to go in there. Now, what do I do about my rates? Right? I need a rate now and a rate to begin with. They didn't give me sort of any of that other than the clue that it's 99.99% disappeared. So basically that percentage is trying to give me the ratio in a sense, right? So percentages in decimal form, right? You just divide, multiply by 100, move your decimal point around. So I want that much of it to go away. How much did I start with? 1, 100%, right? Okay. So 0.00, yeah, 3 zeros and a 1 would be the amount that I basically I have 0.01% remaining of what I started with. And so that number, 0.0001, becomes the thing that is the ratio r over r naught. So I go ahead and my ratio is 0.0001, and that should, if I put all those numbers together, equal 190. I think the tricky part in this problem, because didn't you have another homework problem where they said like a certain percentage decayed or was left or something like that, and it was the percentage that went into the natural log? So instead of giving you a rate then and a rate now, they're just giving you the ratio itself in percent, which I'm sure is bringing up all kinds of post-traumatic stress from ratios in elementary school. day that fractions was introduced to me in elementary school was a bad day. It was very, very bad. That did not sit well. Yeah.
I just have a quick question on what is R and R not again?
They're rates. They're like when you get a sample in, you measure the amount of radiation coming off of it per hour. Right? A rate is always something per time. Okay? So velocity is a measure of your distance per time, right? But in the case, in the context of radiation, this is decays per second. It could be in becquerels, it could be in curies. The example I gave in class was like a decay per second per mass, which is also a type of rate. The key thing was always make sure to get your rates in the same units. So that your ratio turns out to be unitless.
I was talking about the difference for R naught and R which one?
R naught is the one you begin with. It's the one that the sample had to start with when 100% of it was there. And then R is what you have now.
Can you do number 8 on chapter 31?
Number 8. $140, the number decreases to 1/8 the number present initially. Okay, so I can kind of conceptual my way through this one. Because 1/8 tells me that 3 half-lives happened. Because after the first half-life, how much is there? Half, and then a quarter, and then an eighth. So that's 3 half-lives, right? Okay. And so if 3 half-lives took place in 140 days, I take 140 divided by 3. And I have my answer. But there's another way we can math it out. Ends up being more or less the same process. So we can do rates in that half-life decay curve, or as we did it with our simulation in lab, we can do it with number of nuclei remaining, right? So if I want to know the half-life, right, the time is going to be negative natural log n over n naught divided by the decay constant. And so I can solve this for decay constant. I know this in days, and this right here is 1/8. So that'll give me my decay constant, and then I take natural log of 2 divided by the half-life is divided by the decay constant is equal to my half-life. So much longer way to get there, since they gave me such a good ratio of 1/8. Is 140 divided by 3 47? Ish. That's about right. I want to make sure to answer all your questions, but there are some bonus facts with Mr. Balogh I want to teach you. They're bonus, they're extra. If you don't ask me questions, I might just start talking. Yeah, bonus facts with Mr. Balogh? What happens when you fuse hydrogen together? What do you get? You get helium, right? Okay. But what happens when you fuse helium together? helium will fuse to become lithium, beryllium, boron, or carbon. What happens when you fuse carbon together? You get everything on the periodic table up to iron. And that's where fusion stops. That curve that I've been showing you with the binding energy per nucleon, okay? It's got its lowest point or its highest point, depending on which way you're looking at it, at iron. Iron and the isotope of nickel. The best fusion reactors in the universe are stars. And when a star runs out of hydrogen to fuse, it will begin fusing its helium. And to do that, it has to heat up to an even higher temperature. Once the helium becomes exhausted in the core of that star, if it's not massive enough for gravity to collapse it down and heat it up even more, the star will die in something called a nova or a planetary nebula or something like that. But stars that fuse helium and helium together eventually will start producing carbon. And carbon fusion, these are very hot, very massive stars, will produce everything up to iron. You cannot fuse iron together to make anything. The problem is it's at that point in the curve of inflection, and you have no more room to maneuver when it comes to fusion, because after that it's going to be an uphill battle. So that begs a question. Where do the rest of the elements come from? I mean, iron isn't where we stop on the periodic table, is it? Right? So where do all the other elements come from? And why do all the elements have to come from stars? See, I didn't get a chance to teach you about the galaxy and the universe and cosmology, but I know you know about the Big Bang. The Big Bang isn't what you think it is. It wasn't a bang. It was an inflation, okay? The Big Bang is a term that was assigned by the physicist that didn't believe in it. His name was Frank Zwicky, which I think is a pretty funny name. He derided it by calling it the Big Bang, but in physics we call it inflationary theory, right? Where the universe started off hot and dense and rapidly expanded and cooled. And as it cooled, things like electrons and protons and neutrons began to form. It was too hot for any of those things to be in atoms. About 2 minutes after the inflation began, it cooled off enough for hydrogen and helium to form. And then that hydrogen and helium started fusing in the core of brand new stars. And over hundreds of millions of years, we started getting some of the other elements. But again, that fusion process cannot produce elements heavier than iron. Carbon-carbon fusion ends with iron. Iron will not fuse together regardless of how hot you make the core of that star. Stars of that mass and magnitude have so much gravitational pull that when they exhaust the carbon fuel in their cores, there is a sudden collapse of that core. The core kind of does like a rebound on itself as gravity tries to mash all of that matter together, and that rebound causes the most energetic explosions we know of in the universe, called supernova. In that supernova explosion, the other elements beyond iron are created. To be clear, it's not a fusion process. It's a quark glue process. The processes that produce all the elements beyond iron, okay, only, as far as we can tell, only come when a star dies. In that super energetic event that can mash the protons and neutrons together. That explosion scatters those elements into the universe, where they will later coalesce into new stars and new planetary disks around those stars. And the process repeats itself. Hydrogen fusion to helium fusion to whatever. Okay? So what does that mean about everything beyond iron? What does that mean about the copper and the zinc and the platinum and the gold? Where did it come from? Came from the heart of dying stars. Came from supernova. And yes, when I proposed to my wife, I told her that as a symbol of our love, I could think of nothing better than putting a supernova remnant on her finger. That's what passes for, romance and physicists, okay? But I think it goes one step further. It's kind of a, I don't know if epic moment is the right way to, when you know where gold and these other things come from, right? Anything beyond iron coming out of the supernova event. Carl Sagan famously said that we are made of stardust. He's not wrong. The atoms that are in you did come from the hearts of dying stars. I mean, it came from the hearts of living stars to make the potassium and the nitrogen and the carbon and the phosphor and everything else that makes you, right? But there is a deeper connection here and a deeper realization. It wasn't just, you are not made of just stardust. You are made of Big Bang stuff. The atoms in you came from the Big Bang. You are mostly hydrogen. And that existed 2 minutes after our universe came into being. The organization of those atoms that we call you is unique. Has never been seen before, never been will be seen again. And so you are unique. But the very atoms that make up you are effectively eternal. I mean, 13.8 billion years old. Not bad, right? They've got some mileage on them. But they do shine in their brilliance. So, when you're stuck, when you're sitting there, woe is me, when you think you can't do it, remember, you have a pretty good legacy. And I'm not just talking about the biological one, because you do represent the top 1 trillionth of a percent. Biologically speaking, all of your ancestors had a 100% pass on the gene chance. You represent successful mating pairs going all the way back to what? Bacteria? Right? Okay? That's an accomplishment. Like when I'm having trouble in the day, I just go, you know what? All my ancestors passed it on. Right? To make me. And what's more, I'm made of Big Bang stuff. So I better not explode today. Anyway, bonus facts of Mr. Balogh. Things we didn't get a chance to get to. What are your questions? More so about the exam. Yeah.
Can you do a photo electrical thing?
Yeah, I can actually. I've done the month. You want me to make up one or? Give me a metal. Platinum. That's good. Not my fault. See if this is gonna work. Work function for platinum. Okay, so the work function according to homework.study.com. Do I trust them? No. Okay, so two different sites are telling me hyperphysics. Do I trust that one? Oh, AIP. No. AIP I would have trusted. Michigan State University. Okay, so I've got three places that are all telling me it's 6.35 electron volts. You see what I taught you there? Always check your sources. Okay, right? So 6.35 electron volts, right, is the work function for platinum. Let's find the cutoff frequency for platinum. What's the cutoff frequency? Well, in the photoelectric effect, the governing relationship or equation is one of a conservation of energy equation that says that the most kinetic energy any charge can have once it's been kicked off of a metal is going to be the difference between the amount of energy that hit the metal, the photon energy, the Planck's constant times the frequency, minus the work function, the amount of energy it takes to get off the metal in the first place, right? So the cutoff is the limit where we set this kinetic energy equal to 0. So in other words, what is sort of that minimum of photon energy that's necessary to get the charge off the surface of the metal? I mean, we know the photon energy has to be equal to 6.35 electron volts, right? To just get it off. Anything more than that, it'll have extra energy for kinetic energy. So the cutoff frequency and the cutoff wavelength are the frequency and wavelength that happens at. So that means this has to be true. And I can solve for that frequency by taking my work function and dividing by Planck's constant. I would want to use Planck's constant in its electron volt form. I wrote down somewhere. Planck's, so this frequency is going to be 6.35 electron volts divided by 4.136 times 10 to the minus 15 electron volts seconds. So what unit am I going to end up with here? Inverse seconds, which is a hertz, right? The key thing is getting the electron volts to cancel the electron volts, right? If you have Planck's constant in joules, you're going to want to make sure that you have that you convert your electron volts into joules to make sure that you have units talking to units, right? I have no idea what this number is and I really don't care, but this will come out to be something in the 10 to the 14s. 10 to the 13, 10 to the 14, something like that, okay? Hertz, okay? So there's my cutoff frequency, and then how do we tie this into wavelength? What's the connection between wavelength and frequency for photons? Speed of light, isn't it? Because the speed of light is equal to the wavelength times the frequency, and so my wavelength was speed of light divided by the frequency, and I can take whatever my frequency was and find out what the wavelength was in meters. So that's one way to do a photoelectric effect equation. We could solve for, so like, what would be the maximum kinetic energy if we sent a 10 electron volt photon into platinum? That would be 3.65. Did I subtract correctly? 10 minus 6.3, no, 3.65, there we go, okay? So you just subtract, right, to get that kinetic energy. Is there any other thing to do with photoelectric effect? You can find the work function. Like if we know that the maximum kinetic energy is 15 electron volts, and we know the photon's energy was 10, then the difference between those two things is 5 electron volts. That has to be the work function of the material. I think I covered all the bases there. 31, number 6. Yeah, oh, look at that. This author has not updated their language. There's a movement in physics to get away from daughter nuclei. We always talked about in the past parent nuclei, daughter nuclei, that kind of stuff. We're trying to use parent and child now. Let's be a little bit more inclusive. We used to have, in computers, we used to have master and slave devices. Yeah, that changed about 20 years ago. The master hard drive was in control of the data bus, and every hard drive that was connected after that was a slave to that master. I have no idea what they're called nowadays.
Only 20 years ago?
Yeah, yeah. So I worked in IT 27 years ago up till 30 years ago up to 27 years ago. And those terms were still being used to describe the orientation of devices on the bus. Master and slave. It only changed after I left the IT world. Maybe that's what it needed. Maybe they needed me to leave. But yes, it became a very bad. It had bad connotations then and now. That was a tangent. All right. Oh, we were having trouble with this yesterday. So lead 207 is what we end up with, right? And what we're trying to do is an alpha decay and beta decays, right? And the problem is asking the question weirdly. But basically A, B, and C are all about alpha. So an alpha decay, we start with the parent nucleus with its mass number and its atomic number, and I apologize that the symbols for those don't make sense. It's physics after all, right? Why would it make sense? We end up with the child and that plus our alpha particle, which is a helium-4 nucleus. Okay, so what they've told us is we are ending up with lead 207. And they want to know the features of this thing right here. Okay? So where did it come from? Right? If it was an alpha decay and it was lead right here, it was lead 207, right? Alpha decays lower the atomic number by 2, and they lower the mass number by 4. So to get back to where we started, we want to reverse that. We want to add 2 to the atomic number and add 4 to the mass number. So what's 207 plus 4? 211, right? So I'm here, and I want the answers for this. I want this number, I want that number, and I want the symbol, right? So I take my 207 for an alpha, right, and I add 4, and then I add 2 to kind of reverse the decay. In other words, this would have been 211 over 84. I look for 84 on the periodic table. That's polonium, PO. Okay. So that would decay into lead 207-82 plus the helium-4 nucleus. And I double check. Is 207 plus 4 equal to 11? Yes. 82 plus 2? Yes, I got it. All right. And then they want the same thing for D, E, and F, but for the beta decay. There's beta minus, so it's the electron version of it. So in beta decay, what's the pattern look like? We start with the parent. The child has the same mass number, but adds 1 to its atomic number because the electron has a mass number 0 and a charge number of -1. Okay, so we know that lead 207, 82, and we've got to get everything to add up. So what's the mass number going to be on the parent side? It's going to be exactly the same, isn't it? We don't change it, so that's still going to be 207. And then 82 and a -1. It's 81, isn't it? And then what's 81? Tellurium. Yeah. And then I gotta figure out how to type the numbers into the box. Here at the end of all things, a line from, thank you, Bill. A line from Lord of the Rings. What was it anything like you expected, physics? Harder than you thought? Easier than you thought? Easier? Started off really bad, right? Right? Now, a lot of you I've had for the entire year, right? And I'm the only physics professor you've ever had and hopefully will ever have. Because your journey in physics is at an end, right? You're ticking off a box and moving on and doing the things that are more important to you. Great. But I'm just curious why you say easier. So this is like your evaluation of me, and I know we're doing this face-to-face and not anonymously and all that kind of stuff, right? But I guess what I'm digging at, what did I do right? What did I do wrong? What can I do better? What advice would you give to students coming in? Like if somebody you knew was going to be taking physics, like what's some general advice you'd give? So like, what's that? Beyond that, like what are some things we could do better at Fresno City College? What are some things
That's too broad of a question.
That's too broad. Okay, fire half of the professor. I guess what I'm getting at is why do you say easier than you expected? Because you survived and you didn't expect to survive?
I think as everybody makes it out to be really scary, and like granted we are taking the algebra version of this course, which thank God, but
which I actually think is harder.
Really?
Yes.
Okay. I don't like calculus, so but
Calculus makes physics a lot easier.
But I mean, it didn't just turn out to be algebra most of the time. So.
What was the workload like? Did you expect it to be more or less?
More.
It ended up being more?
No.
No, it ended up being less?
Yeah.
Okay. That's good.
Which is great.
Was part of that the fact that the labs didn't give you any extra stuff to do outside of the labs?
Yes.
The labs are pretty laid back and easy, and we specifically designed them to be that, right? Like, we know how to make your life really, really bad, right? Okay. But they're amongst our physics teachers, we didn't see any educational value with that amount of torture, right? Exams, were exams easier than you thought?
Yeah.
Yeah, okay. If there's anything that I maybe do a little bit wrong is that I don't make my exams hard enough, but at the same time, I keep seeing, over the years I've changed the style of the exam, the level of difficulty of the exam, and it seems like no matter what, I get the same grade distribution.
I really like how your exams are formatted.
How so? Like in specifics?
I personally really like the 2 points per question.
Mm-hmm.
Because I find that in other exams, things are graded differently and not as uniformly as yours are graded, and so I end up losing more points for arbitrary things.
Like an all or nothing
Mm-hmm.
Yeah.
You're either right or you're
Mm-hmm.
You don't wanna run into something, you're like, oh, I know this one, it's not worth anything, and then you run into another one like, I don't know this, that's half my grade.
Yeah,
So the consistency that they're always the same relative value.
yes.
Yeah, no, I hear you there. Those types of exams that weight problems differently haven't been shown to have any effect beyond
I think the
Scary
consistency of the whole course is
Yeah.
really helpful.
need consistency, but
Yeah.
No, so like, we always know where to go for homework, like we always
Mm.
know like when it's due, like what day we're gonna discuss what.
Oh, so like
I
always,
think that's
always
what-
making sure that exams happen, say on a Thursday,
Yeah, or
and
like
the review is always right
there's
before.
class on Fridays,
Yeah.
like every single time, and then I feel like that kind of like takes away from like the anxiety of like, oh, am I missing anything? Like you know exactly what is coming, so you know how to plan for it. It makes it easier to juggle with other things.
And we're posting new exam topics too.
Mm. Yeah.
Also the expediency at which you post lecture videos is
Yeah.
Oh, yeah.
appreciated for those of us chronically ill people.
I don't know what's gonna happen with lecture videos.
Aren't they doing the accessibility?
Yeah,
Limiting
so-
the canvas?
Here's how you sue Mr. Balogh.
Yeah.
My videos are not captioned.
They have generated captions which are tolerable.
They're getting better.
Tolerable.
When I first enabled that,
And,
when I first enabled that, it would every like 10 words put music notes when I was talking. I was like,
That's really funny.
that is not an acceptable form of captioning. Especially for those of you that people that need that captioning. There's actually a federal standard for the captioning accuracy, and Google is not meeting it. I'm hopeful that AI will finally get to that point where it can just do it, just nail it every single time, but we're not there yet. I am very careful to make sure that you may have noticed, my videos are never posted on a campus website. Have you noticed that?
Yeah.
There's 2 reasons for that. Number 1, I own it, the school does not. It's my intellectual property. If they fired me or if I moved to a different school or anything, it goes with me, it doesn't stay with the school. Number 2, so MrBalogh.com. But the other thing is, if it's posted to a school website, it must be equal to the accessibility standards, which I am in support of, but I don't have 6 extra hours in my day to go through and caption a video the way it's supposed to be captioned. Like I just don't, and we don't have people that do it for us. And so I'm always in that tricky spot, you see, like the clips technically that I play in here should be captioned. And I need like a semester to go through and like read, it's just, the workload there is amazing. So I'm skirting under the radar in some places, and I am definitely not in compliance in others.
You have your caption book.
What's that? Yeah, I do have my caption book, which again is my legal way out, but it's not effective for somebody that needs that captioning. So
It only gives the answers like half the time, so.
still, reading a book and watching it doesn't do it. What advice would you give to a student that's got to go through physics? Like knowing what you know now.
Don't miss lecture.
Don't miss lecture.
Go to Grasp every Friday for help. Just do your networking.
I am not allowed, I want to put in the schedule that this is a Tuesday, Thursday, Friday class. But I can't, because technically that Friday is optional, and so we can't assign a unit to it, and that kind of stuff, right? But I don't know how to get out front of that far enough to say, look, try to reserve Fridays for,
Maybe on Sunday.
Okay, but
You can do that.
I can, but like, this is one of the reasons I don't like doing extra credit very often. People that have to work on that day, right, are denied the incentive simply because they have to work. But if when they're signing up for classes, it's communicated, then they can make choices,
Oh.
right?
So like adding in
Yeah,
potentially to the class registration thing.
Right.
Yeah, the description.
right, and we can kind of, well, that description box is limited and we're required to say that you have to buy an extra package. They should never put it in charge.
I
Blood.
think that's right.
Blood will flow. Like seriously. Starting with the governor of the state, working down to this college, blood will flow. Because it's just the way we do things, so inefficient. Anyway, and I always know I'm right, but I'm definitely not. So go to class. What's that?
I said step one.
Step one, go to class. I think, surprise, right?
I feel like rewatching the lecture videos is really helpful for me.
Yeah. I'm hoping that they can continue. My software is dying. You guys have seen it this semester. It's just like it blanks out and it just gets. I'm actually recording 3 versions of this. And on multiple times this semester, I've had to rely on the 3rd version because the other 2 failed. Like it's just weird how it's kind of fallen apart a little bit. I know part of that's sort of the way I do it. Like I could get everything onto my iPad and do it that way, but the iPad is so limited in so many ways compared to other. Anyway, it's rough. So here's a different question for you. I'm an old white guy, and I stand in front of the class and I say, "Well, you really should go to class." Students don't believe me anymore. So how do I tell you guys? How do I communicate to you guys that that's important and have you believe me? Not you specifically, but like your age group compared to my age group.
We had this conversation and laugh that literally just start out by insulting old white guys.
I don't mind insulting myself. I'm good at it.
If they don't listen, it's kind of something you have to learn on.
Kind of something they have to learn. It always kind of comes down to that, doesn't it?
Yeah.
Right? You learn from the school of hard knocks. I always say, knowing is how you know stuff. Like, it's such a stupid phrase, but it's actually very deep, right? Because you can be told something over and over again, but until you, like, experience it, it may not carry the weight.
I feel like you get like plenty of opportunities to do well in the class, so it's
Right.
like at that point if you're just not gonna show up, like you're just not gonna show
I
up.
think you're doing everything you can do. I think our generation's average school work ethic is lower, but you're doing everything you can do to encourage those willing to come.
Like the
I'm gonna disagree with your first part of your statement.
Which was
The school work ethic being lower. I think it's different. Like, I've got lots of evidence that it's different. I don't think it's lower.
different now.
The way that people learn now has not caught up with the way we deliver information. And I am still very much in that old form of give information, but you also notice that it's not just always lecture. Like, I'm always challenging, asking, getting you to talk to each other, doing all of these active learning things. I could be doing a whole lot more or less, whatever, right? But like, the way into your brains is through your phones. And it didn't used to be that way. The way into your brains used to be the book. And I see that actually coming back. More of you, believe it or not, are reading the book. I was actually shocked this year at how many of my students called me on, but Mr. Balogh, I read in the book this. I used to be able to bluff my way through and nobody read the book. It was great. Now, right, I've got to read the book again.
That's because we know how to find information elsewhere.
Yeah.
We don't
The skill
have
at,
access.
so we went through the entire 10-year period of students believing everything on the internet. And now you have skepticism, like the lessons they taught you in school about how to find references and back up your data. We actually see that coming into effect, which is great.
You showed us this today too.
Yeah, I patterned it, I modeled it. The time has come to say goodbye. So I'm gonna leave you with two references to pop culture and literature here, okay? Because I'm terrible at saying goodbye, and so I rely on others to do it for me. On Broadway, there's a hit musical called Wicked. And if you're not a Broadway person, I don't blame you. But if you're going to watch a musical, I really recommend Wicked. It is a fantastic story. It's the story of the Wizard of Oz, as told from the point of view of the witches, the Wicked Witch of the East and the Good Witch of the North. They turned out to be friends from college. And they just give you the entire backstory, okay? And the music is great, the story is fantastic, but at the end, the two witches, because of what's going on, are having to say goodbye. And this is a verse and the chorus from a song, okay, that's entitled "For Good." I'm not going to sing it, those of you that are worried. So this is Glinda, the Good Witch of the North, singing to Alphaba, the Wicked Witch of the East. I've heard it said that people come into our lives for a reason, bringing something we must learn. And we are led to those who help us most to grow if we let them. And then we help them in return. Well, I don't know if I believe that's true. But I know I'm who I am today because I knew you. Like a comet pulled from orbit as it passes the sun. Like a stream that meets a boulder halfway through the wood. Who can say if I have been changed for the better? But because I knew you, I have been changed for good. Well, yes, I didn't. The other emotion I want to leave with you, right? I've taught you a lot of things, right? And a lot of it's been physics as required by the state of California, and that's really what you paid for, right? When you came. Many of you got a whole lot more because you were willing to trust me. And you told me things about your lives and your situations and all of those good and wonderful and terrible things that have been happening to you for a year. And you're going to go off and you're going to be great and you're going to be bad and you're going to be all kinds of things, right? Life has a lot of events in store for you. But let me leave you with this thought, and I have quoted this person a lot in the course of our 2 semesters together. The preeminent philosopher of our age, Winnie the Pooh. And I always hate this part of the book. This is the part of the book where Christopher Robin is growing up. And he's going to leave. He's going to go to school. And he's trying to explain to Winnie the Pooh why they can't be together anymore. This is what he says. If ever there is a tomorrow when we're not together, there is something you must always remember. You are braver than you believe, stronger than you seem, and smarter than you think. But the most important thing is, even if we're apart, I will always be with you. Thank you for being a part of me. I hope you take the best part of this class and make it a part of you and go off and be amazing. Have a fantastic future. I'll see you on Thursday to put the test to you one last time. You have your quiz sheets, bring them up here.
Yeah.